let me start so that we can get through this, and I can give you some time towards at the end of the period as well. So this, I have, I think it's 2.5 questions. They are in the textbook. The half question is I take the second question and I say, what if it's this one, okay? So I would suggest you write these down as sample questions. It didn't really seem worth typing it out for just 2. And I have a video at the end. It is classic 1970s. We can look back on it now and laugh at the zaniness that was the 1970s.
I think we already seen this.
Yes. Okay. Okay. So.
Better not have a swear in it like yesterday.
No, there's no swearing around it. Don't worry. No swearing. Okay. So we're going to talk now about. You know what? This should have happened before. We should be doing this before the frictional coefficient lab. So this might help you with the frictional coefficient lab.
Oh.
That's okay. Let's go through this. So I've got a girl, not a girls, a girl. A girl sits at. Making it worse. A girl sits at the top of a frictionless, snow-covered hill on her inner tube. If the hill is inclined at an angle of 25 degrees to the horizontal, what would be the girl's acceleration due to gravity? Now remember, this is frictionless, right?
Yes.
Okay, so, should I just wait here while you write down?
Yes.
Okay, I'm going to do that, yeah. Do you remember what happens on a frictionless hill? What's the deal?
You can use this special formula.
The special formula. Do you remember why, Ryan?
Because there's no friction.
Well, okay. So on a frictionless hill, right?
Something cancels.
The only force that is acting is Fd, right?
Yep.
There's also, of course, there's the weight force and the F perpendicular. Oh, sorry.
It's okay.
Okay, so here's example number 2 from the book. This one's way back. Now, there was this daredevil crazy guy named Evel Knievel. Yes, you might have heard the name. His son is Robbie Knievel. He was a daredevil as well. Evel Knievel is now dead. Apparently, he broke every bone in his body at least once.
That's cool. That's cool.
This is him jumping. If you've ever been to Las Vegas, it doesn't look anything like this, but he decided he was going to jump the fountains at Caesar's Palace in Las Vegas. Just because they were there. Okay? So this is an Evel Knievel question, and after it, I'm going to show you an Evel Knievel stunt. So.
That's the video?
Yeah, something like that. Evel Knievel is. Let's do the question first, and then we'll talk about it.
You don't watch that palm side.
Evel Knievel is driving his motorcycle up a ramp inclined at 30 degrees to the horizontal before jumping over a row of cars. If there's a constant frictional force of 1,000 newtons on the ramp, determine the force that the motorcycle engine must apply to accelerate up the ramp at 1/3 g. So there's lots going on here. Okay, so I'll let you write that down. Okay, so let's draw a free body diagram here. So we'll just draw it as a box because I'm a bad drawer.
Okay.
Weight force. F perpendicular, F normal, FD, and there's also a friction. Now he's going up the ramp, so which way is friction? It's down. And I guess he's applying, or the motorbike is applying a force to the bike to accelerate it up the ramp, right? Okay, so we know, we need to know what's the force the motorcycle engine can apply to accelerate up the ramp at 1/3 g. So the first thing I need to tell you is, what does 1/3 g mean? Well, 1 g is equal to gravity, 9.8 meters per second squared. So 1/3 g is simply going to be 9.8 divided by 3. Okay? Sorry. So that's like 3.27. Right? Did you have a question, Kyle? Okay, so now we could say that the net force is mass times acceleration. So the net force required is the mass of 250 times that 3.27. 816.7 is the required net force. Am I going to need more than 816.7 newtons out of my engine?
Of course,
How come?
because you have to get some air.
No, that's the net force to get said air.
Oh,
But you're right, I need more than 816.7. How come?
to get more air.
Because of friction, I have to overcome friction, and I have to overcome the downward force, right? Like if it was just friction, I would need 1,816.7 newtons, right? I need 1,000 newtons to overcome friction and an additional 816 to accelerate so that I don't break every bone in my body. So that net force is made up of what forces? Well, it's made up of the applied force plus the friction force plus the FD. Oh, I haven't figured out the FD yet, have I? Did you leave yourself some room?
Makes sense.
FD is equal to mg sine theta. Don't you wish you had fancy paper where you can move things around like I can?
I can do that.
Yeah.
It's called an eraser.
It is called an eraser, yeah. The mass is
All right.
250 times 9.8 times the sine of theta. Oh yeah. Change that to 30.
So would there ever just have to find data?
You might. I'd have to give you like some triangle dimensions to find the angle, but most of the time they give it to you.
That means on the test he's
1225.
Exactly.
Is that 1,200?
Yeah. Anything, oh, we know what FF is, right? Oh, okay, so the required F net is my 816.7. The applied force is what I'm trying to solve for. My friction force is that 1,000, but it is negative. And my FD is also negative. In other words, my FA is a total of 816.7 plus 1,000 plus 1225. It's a lot of force. (3041.7 newtons). That's how much applied force Evil needs. I'll pause and let you think about it, Todd.
Holy crap.
How come you didn't take the 816.7?
How come I didn't make it negative? The FA, the net force, has to be up the ramp, doesn't it?
You move the other two over.
I moved them, and then I just rewrote it. Yes, like I always do.
Yeah, all you have to do is that.
No one likes the FA on the right-hand side.
No. That's stupid.
Now, how often do you think is it going to give you that friction force just as like a value in newtons?
Not very often.
Not very often. That's the one thing I don't like about this textbook question. So here's the extra half question, which is suppose that rather than 1,000 newtons of force, that the frictional coefficient is 0.15. Let's just say it's 0.15 rather than 1,000. How would you do it? Well, the only thing that's really different is going to be what? I need, these two are going to be the same, right?
Yep.
The only thing I need to find my FF, right?
Yeah.
Okay. So to find the FF, do I just to wait there for you to write that down?
You go back.
Yeah.
Oh, what's the FN?
Okay, so I need to find that FF. So mu equals FF over Fn, but I don't have my Fn yet, do I? Fn is equal to mg cos theta. So that's going to be 250 times 9.8 times the cosine is at 30 degrees, I think it is. 250 times 9.8 times cos 30. No, we did sine 30. 2121.8. That's just the Fn. And mu equals Ff over Fn, 0.15. So basically, I just take that value and multiply by 0.15. 318.3, which seems more reasonable. 318.3. Now, in the lab, I think I gave you this formula. I said FF equals mu mg cos theta. Remember that? Okay, so that comes from this, right? Here's my Fn, the mg cos theta, but then I take that value and I multiply by mu, right? So, I mean, if you want, you can write that formula down, but it's really just those two steps combined together.
Okay, so on like a test exam, if you did it with the two-step.
Oh, that's perfectly all right, absolutely. Perfectly all right. So now I basically have to do what? I got to do all this again, right? And I don't know if you want to copy it over or not. I'll leave that up to you whether you want that. So instead of 1,000, it's 318.3, right? And that number changes, obviously. Now, does that seem like a more reasonable kind of question? It does to me. Like they're going to give you the mu value, they're not going to give you the FF value. Okay? 2360. Now, here's a few in the book if you want to try. Page 196, numbers 1 to 4. Page 224 is numbers 6 to 10. Those are some fairly challenging questions that you can try. I need to take care of equilibrium as well before we have our test. I'll have a look right away and sort of, is there, I'd like to start tomorrow if I could. No, start like the next topic. Right? Yeah, no.
So I just have questions, like those extra functions.
But first I want to show you this, because this is my favorite video to show in grade 12.